Sir, good afternoon, sir.
Good afternoon, madam.
Okay. Sir, shall we start, sir?
Can we wait for a couple of minutes more?
Yes. Okay, sir. Okay.
Yeah, because there is a wagon selling something on the street. I'm on vacation, so I'm at home. So all these ambient noises from the environment is going to be there all the time. So
Okay, sir. Okay, sir.
yes. Let's wait until that wagon passes.
Okay, sir. Okay, sir.
Yeah. Madam, I think we can begin.
Yes, sir.
Yes.
Very good afternoon, sir. Yeah, a formal welcome, sir.
Yeah. Thank you.
Good afternoon to all. I welcome you all for fourth day of FDP on development of materials, characterization techniques, and their future prospects, conducted by the Department of Physics under DBT Star Status Scheme, Sri GVG Vishalaji College for Women, Udumalpet. Today's session on voltammetric and impedance-based electroanalytical tools for characterizing energy conversion and storage materials will be given by Dr. Anandaraj Singani, Assistant Professor, Department of Chemistry, IIT Kanpur, Associate of Indian Academy of Sciences, Bangalore. I'm happy to introduce today's resource person, Dr. Anandaraj Singani. Dr. Anandaraj Singani is an assistant professor in Department of Chemistry, IIT Kanpur, Associate of Indian Academy of Sciences, Bangalore. He completed PhD in Science from ACSIR, Karaikudi, Tamil Nadu in 2018. MSc in Chemistry, University of Madras, Tamil Nadu, India in the year 2013. BSc in Chemistry, University of Madras, Tamil Nadu in the year 2011. He had experience of working as assistant professor SRM IST, Kottangulathur, Tamil Nadu from April 2023 to August 2023. Assistant professor Waseda University, Tokyo, Japan, in the year April 2021 to March 2023. JSPS Postdoctoral Fellow, Waseda University, Tokyo, Japan, from January 2019 to March 2021. He placed on the list of the world's top 2% scientist database released by Stanford University in the year 2020 to 2023. Associate of Indian Academy of Sciences, Bangalore in the year 2023. He awarded highly cited author in the year 20 from RSC Publishing. Faculty Fellowship from SHER India 2022. Anik Faculty Award in the year 2020. JSPS Postdoctoral Fellowship in the year.
Excuse me, madam. I think it's going to go on for a very long time. Okay, can we please conclude and make it short?
Okay, sir. Okay, sir.
Yeah. Sorry.
We are very much happy to invite you for this lecture, sir.
Yeah. I'm also happy. Yes, but it is going to take a lot of time. So please conclude.
Okay, sir. Okay, sir.
Yeah.
The IS is yours. Thank you, sir.
Yeah. Thank you. So first of all, I would like to thank Dr. Kavita for reaching out to me about this faculty development program. It is always a pleasure for me whenever I am asked to speak about the things that I love. So I'm an electrochemist. From the introduction, you could have guessed that I did my PhD in CECRI, the Central Electrochemical Research Institute, the only institute in Asia that is entirely dedicated for electrochemical science and technology and research based on that. So being an electrochemist, I am always fascinated by the changes that the transfer of electrons across interfaces that they impart in different phases of materials and matters. So that said, as you know that, as you could also guess that when I am interested in electron transfer across interfaces, you could also guess that I am also interested in energy storage and conversion materials because the future depends on it. And we are living in the future, which was for some people 30 years before was nearly impossible. So just think about the way how these portable electronics have grown and revolutionized our day-to-day lives. So these are some fascinating things about electrochemical energy storage and conversion. And I also would love to talk about the techniques that are used in characterizing the materials that are used in those electrochemical energy conversion and storage devices. So in today's talk, I was asked to give a brief overview, fundamental overview on different voltammetric and electrochemical impedance-based electroanalytical techniques for characterizing these materials. I initially thought of giving you a brief overview almost on all the 5 different impedance techniques available, but in want of time, I will not be able to do so. So if you are having any queries, or if you need any clarification on any of these techniques, you are welcome to write me an email. Whenever I get time, whenever I read your emails, I will definitely reply. So with that, I will just begin. So today's talk will be having two parts. Part one, an introduction to different voltammetric techniques, and part two, an electrochemical impedance spectroscopy, the fundamental one. Okay. So before going into voltammetric technique, let's recall the things that we learned or we are learning in our MSc physical chemistry section. The advanced electrochemistry unit has this thing, and even some universities have this thing in UG level syllabus too. And in some schools, they also teach this in schools in some syllabus. So this is nothing but the world famous Nernst equation, which basically gives you the relationship between the cell potential, which is E here, with the reaction quotient of the reaction that we are studying. So the only requirement is that there should be an electron transfer to correlate the cell potential with that of the reaction quotient. So the reaction can be anything. It can be as simple as proton reduction to multiple step complex kinetics having reactions such as OER and ORR, oxygen evolution reaction and oxygen reduction reaction. So what we are going to remember from this equation is that, so for every single change, every tiny change in the concentration of the reactants and products that are involved in the reaction that we are going to study, there will be a change in cell potential. And how this relationship can be used in order to understand the reaction that we are interested in on the material that we have when it is placed inside an electrolyte, forming an electrode-electrolyte interface. So this is one of the basic cornerstones for voltammetric techniques. So how it is derived, you all know, so I'm not going to take much time here. So let's just skip to voltammetry. Voltammetry is nothing but studying interfaces in terms of electric current by applying constant potential for a fixed amount of time, or a potential ramp at a desired rate. We call that scan rate. So depending on how we apply this potential, these voltammetric techniques can also be further classified into two categories. One is potential step techniques or constant potential techniques, and the second one is sweeping techniques. I guess you all know about this. Both of them have their own advantages and disadvantages. Let's see a few simple potential step techniques and how they can be used in characterizing energy conversion and storage materials. It's the step potential voltammetry. This is nothing but the chronoamperometry that we use in our labs to test the endurance of a particular material that you have for a particular reaction. For example, if you have developed an electrocatalyst for performing oxygen evolution reaction or hydrogen evolution reaction, so for testing its stability, what you do is either you apply a steady current or a steady potential and see how the interface reacts. So when you say step potential voltammetry, what we are doing here is that you are having your electrode inserted in an electrolyte solution represented by this graphical sketch, where the electrode immediately forms a double layer because of the surface charges existing. And when you this is when where you are at potential E1 for an arbitrary reaction such as this one, A plus B getting reduced to B, and conditions stated here. So conditions are so simple that at E1 A plus is stable, which means that this reaction cannot happen. At E2 B is stable, which means that the reduction of A plus is so vigorous that A plus cannot exist in that potential. We also added one more condition that whatever potential you apply beyond E2 is limited by mass transfer. Mass transfer is referring to the transfer or the amount of electroactive species that are approaching the electrode-electrolyte interfaces at a given point of time. So this kind of reactions are called mass transfer limited or diffusion limited reactions. So let's see what happens when we step up the potential. It can be stepping up or stepping down. It can be anything. So the name comes from step potential. The step potential voltammetry comes from the procedure we apply. It was earlier in OCV, or open circuit potential, and we step that potential up to E2, where the reduction of A plus is so vigorous and the formation of B is highly favored, beyond which the reaction is limited by mass transfer. Okay, so when that happens, we also let that this interface, to stay at this potential E2 for a sufficient period of time. So with increasing time, the depletion of electroactive species at the interface is also increasing, which means that the electrolyte adjacent to the electrode surface is now completely wiped off or depleted from the active species concentration. So we have successfully created a concentration gradient. So this will trigger another mode of mass transfer, which is called the diffusion, one of the three modes of mass transfer in solution-based electrochemistry. So when this diffusion rate is controlling the rate of reaction at the electrode interface, that is when we call this reaction mass transfer limited reaction. So for such kind of reactions, if you plot the current response of this interface against time, you will see a current response such as this one. So this is the classical chronoamperometry technique used for a diffusion controlled reaction. If the reaction is not diffusion controlled, let's assume that the reactant is in a very high concentration. So in that case, the depletion of those active species concentration at the interface is going to be very, very minimal or almost negligible. In that case, all that you will see here is a straight line if your electrode is stable enough, and that's what we see with most of the stable HCR and OER electrocatalysts. Okay, so that's step potential voltammetry. Now you have an idea why we call it a step potential voltammetry, because we are stepping up the potential. And there is a second technique that is called double potential step chronoamperometry or voltammetry. In this case, what we do is that we have the same arbitrary reaction and same conditions, but we are going to add one more step. That is, instead of just staying at potential E2, we are also stepping the potential back to E1. Just a second. I'll be back. Just a second. Yeah, I'm sorry about that. So my daughter was entering the hallway and I couldn't. Sorry about that. Yeah. So can you see my slides? Yes, I hope you can. Yeah. Yeah, thank you. Yes, thank you for confirming. So where were we? Yeah, double potential step chronoamperometry. So in this case, what we are going to do is that we are not just going to sit at potential E2 for a sufficient period of time. Instead, we are going to reverse back to the initial potential. So the main application of this particular method is to test the electrochemical reversibility of the reaction we study, and also the endurance or stability of the electrode for any change in the polarity. For example, at E1, the oxidation of B is favored. At E2, the reduction of A plus is favored. If this polarity change affects the electrode, it will not have the same performance when you measure the current versus time response. So if you just integrate the charge under this curve and charge under this curve, if they are the same but with opposite sign, you will assume that the electrochemical reaction, whatever we are studying, is exactly reversible. I'll tell you, this method is far better than the cyclic voltammetry, because cyclic voltammetry, despite being the easiest one and the most commonly used one, it has lot of flaws that people usually don't know about. But this double potential step chronoamperometry is the best method. I'll explain why when I talk about cyclic voltammetry. And yeah, so the next one is chronocoulometry. Chronocoulometry is nothing but it is just the step potential voltammetry or the double step potential chronoamperometry. Instead of plotting the current against the time, what we will be doing here is that we will plot the charge against time, so that it will give us how the interface is behaving when we charge and discharge. So this is suitable for characterizing materials that are used in energy storage devices like capacitors and batteries. So this is what we call the classical galvanostatic charge discharge curve, right? So that is how the step potential techniques are so good at in characterizing your materials that are used in energy conversion and storage devices. Other than these methods, in step potential techniques, there are also many other methods that can give you an elaborate information about the interface. I'm sorry again, just she's crying. I'll have to, yes, just a second. Sorry. I'm extremely sorry again. She wants to sit with me here while I make my presentation. Yeah, I'm sorry about that, and I hope there will be no more interruptions. Yeah. So other than this, I was talking about sampled current voltammetry and other step potential techniques, which can also be used in characterizing your materials for better understanding how it behaves when there is an electron transfer, when there is a charge discharging, whether it could be a combination of both Faraday process or non-Faraday process, or it could only be a non-Faraday process. Regardless of all these things, step potential voltammetric techniques are wondrous tools compared to the sweeping techniques. And this is what I was telling you all about the sampled current voltammetry. So in this case, what we do is that we perform the same reaction. So instead of jumping right away to the potential E2 beyond which the reaction is mass transfer limited, we make incremental steps. So from E1 to E2. So let's assume this condition now. So when you jump up from E1 to step 1, there is still no reaction, which means that if you record the current versus time response, you will still see no current response, no Faraday current response. When you go to step 2, the reaction proceeds very slowly because you have now given the bare minimum of potential required for the reaction to begin. So in that case, you will see a current which is decreasing with time according to Cutler's equation, but the current won't be the highest one because we have still not reached the potential at which the reaction will be limited by mass transfer. So for every single step of increment you do with the potential from E1 to E2, you will continue to see an increase in current with time. So once you reach 4, the step 4, which represents the diffusion limitation potential or potential of diffusion limitation, EL, then you will see the highest possible current that you can see with your electrode for the said reaction. So even if you go beyond 4, where the reaction is limited by mass transfer, you will not see any increase in current. You will see the same current for steps 4 and 5. So this is giving an enormous amount of information about how your reactions are being carried out and how your electrode is capable of delivering this reaction, and you could also do some kinetic analysis with this. So the sample current voltammetry is nothing but now you have several CA responses for several intermediate steps. So you plot them all together and choose a common time line and sample all those current and plot them against the set potential. So this is very similar to what we get for an LSV, linear sweep voltammogram. But the only thing is that this is far, far better than a linear sweep voltammogram. Reason is why? Because in case of linear sweep voltammogram, we are not letting the interface to stay at a particular potential, even at the slowest scan rate possible, for sufficient amount of time to ensure that capacitor exist to cease to exist, and the IR drop is not an issue anymore. But in the case of sampled current voltammetry, even though there will be IR drop, the capacitance current contribution will be eliminated. So whatever you see will be a pure Faraday current only with IR drop. So if you know the uncompensated resistance value, you can simply manually perform IR drop compensation, and you can get only the Faraday current that is unaffected by double layer charging or the capacitance current. So that is the beauty of sample current voltammetry. So these are some techniques from step potential techniques category. Now we will see some sweeping techniques. So I'm going to give you an overview about the linear sweep voltammogram and also cyclic voltammogram, which you all know very well. So let's again, one more time, revisit the Nernst equation. The Nernst equation tells us that the cell potential is dependent on reaction quotient. It can be anything. Okay, so let's assume we are studying a reaction which is following one electron transfer, and it appears to be reversible. But how will you say whether a reaction is reversible or not by performing an electroanalytical technique, medieval electroanalytical technique like cyclic voltammogram? So these are the conditions. So for Nernst equation says that for any change in potential, the concentration will change, right? So likewise, if there is any change in concentration, the potential will also change. So when the concentration of the products is equal to the reactants, we say that that potential is the halfway potential, or which is almost in most of the cases when the reaction is absolutely reversible, equal to the reversible potential or equilibrium potential of the reaction what we study. If the reaction follows the conditions put forwarded by the Nernst equation, we call those reactions Nernstian reactions. So which simply means that this reaction is perfectly reversible no matter what. So that's what it means. So let's see what is linear sweep voltammogram. And linear sweep voltammogram, as the name suggests, so again we are going to step the potential from one point to another point. Instead of directly jumping from here to here, what we are going to do is that we are going to drag the potential at a constant rate for a fixed amount of time and see what happens to the interface in terms of current. And we plot the current against the potential. So that's what linear sweep voltammogram is all about. So let's imagine we are starting at V1 and we are dragging that potential to V2 at a given rate. So that is called scan rate. So as you do that, when you reach somewhere here, the potential is the bare minimum for the reaction to start. And that's when we see the onset of current, and we call this potential onset potential. So as we continue to increase the potential, we also see an increase in current as long as we increase the potential up to this potential, which is called the peak potential, because beyond which the reaction will be limited by the amount of electroactive species that are diffusing from the bulk of the solution to the electrode-electrolyte interface. So that's what we call in solution electrochemistry the diffusion limitation. So this also will keep on show a declining trend in current until the diffusion rate of diffusion of electroactive species is equilibrated by the rate of electron transfer at the interface is equilibrated by the rate of diffusion of electroactive species. That's where you see a plateau. So this is the very common or classic like linear sweep voltammetry or voltammogram of a diffusion control reaction. So this is called linear sweep because we have maintained the direction of sweeping or dragging from one point to another point. So when you do the same in the reverse as well, over time at the same rate at which you drag this potential, that is called cyclic voltammetry. So for increasing the potential from V1 to V2, you see reduction, and then V2 to V1 back, you see that oxidation back. So this is what you get as a cyclic voltammogram. So this cyclic voltammogram will have lot of information compared to the linear sweep voltammogram. The linear sweep voltammogram has given us the onset potential, peak potential, and also limiting potential. But if you see this peak-shaped voltammogram, you can see that the peak to peak potential distance also matters. And we also get some a potential which is called half-wave potential or E half for a reversible reaction. That potential is equivalent to E0, which is nothing but the standard potential or reversible potential or equilibrium potential. You can call it as whatever you want to call it. All are the same in most of the cases. So this is cyclic voltammetry. So if you see, only cyclic voltammetry and linear shift voltammogram of a diffusion controlled reaction will be giving a peak shaped voltammogram. In the case of cyclic voltammetry, it is even called a duct shaped voltammogram. So why is it so? That's the next question. Why should it give a peak? So that's the question. So to understand this, you must understand the concept of double layer, electrochemical double layer, to be specific. So when you don't have any reaction going on, you have just inserted an electrode, and the electrode is in the electrolyte solution, which is also having the electroactive species. And as soon as you have immersed the electrode into the solution, the electroactive species, which is usually oppositely charged, will get absorbed over the electrode surface, forming an electrochemical double layer, establishing a potential which we call the open circuit potential. So once this has happened, and you are going to now apply a ramp of potential forward, and you are going to reverse the same to back to the original position. So this is cyclic voltammetry, right? So let's see what happens to the concentration profiles of the reactant and the product as we do that. So for this purpose, let's take an example of the reduction of ferrocenium cation to ferrocene. Okay, this particular redox couple is well explored in fundamental electrochemical kinetics or electronics to study the reaction rate or electron transfer rate. So this reaction is perfectly reversible, which means that the peak-to-peak separation will be close to 59 millivolt as dictated by the Nernst equation. So let's assume at A, ferrocenium cation is stable at A and G. At D, ferrocene is stable. And this reduction starts as soon as you reach this position, and B is the potential where it meets the halfway potential for the reduction. And C is the potential for the peak reduction current. And when you go to D, the reaction is now completely limited by the mass transfer of ferrocenium cation. So when you come back to E, now the reaction is controlled by kinetics, and it is called the halfway potential of oxidation of ferrocene. When you reach the potential F, that is the peak potential for the oxidation of ferrocene back to ferrocenium cation. So when you are at point G, that is the potential where only ferrocenium cation can be stable. So these are the conditions, and we have established. So let's assume the concentration profile. Let's picturize the concentration profile as given here. So at A, I told you that ferrocenium cation is stable, which is the only species that is populating the interface, right? So its concentration is given to be equal to the unity. So as soon as you reach the halfway potential, where the reaction is still controlled by the kinetics of the electron transfer, you will have the equal amount of ferrocene and equal amount of ferrocenium cation. Once you reach position point C, there you have almost depleted all the ferrocenium cation that are immediately available on the electrode surface. So the further reaction, what will happen, since it is keep on depleting, the further you will see a decline in current until you reach point D. At point D, there is literally no more ferrocenium cation. All further reaction is limited by the ferrocenium cation that is diffusing from the bulk of the solution. So that's why you see a plateau here. So now the interface is highly populated or entirely populated by ferrocene. So when you switch the scan and go to point E, which is the halfway potential for the oxidation of ferrocene to ferrocenium cation, you will have equal concentration of ferrocenium cation and ferrocene again here. So once you go beyond that, the concentration of ferrocene will decrease, resulting in a similar declining behavior in current, giving you the peak-shaped voltammogram. Once you reach point G, this is the potential where only ferrocenium cation is stable, so you get a peak-shaped voltammogram or a duct-shaped voltammogram. So that is the reason why we get duct-shaped voltammogram or peak-shaped voltammogram. So this is a phenomenon which has been used by analytical chemists for over a century to study the nature of the electrode, nature of the reaction that they study, nature of the solvent, how the electroactive species is interacting with the solvent, how the electroactive species is interacting with the electrode surface. just because of this particular phenomenon. So just by increasing the scan rate, decreasing the scan rate, you can study so many things like peak to peak, what happens to peak separation, what happens to peak current, what happens to the onset potential, halfway potential, all these things. They are all going to give you vital information about how your electrode electrolyte interface is behaving. So that's why this phenomenon is so important in solution electrochemistry, particularly when your reaction is limited by mass transfer. Let's see. So this is all happening when we have diffusion limitation. So what happens when we eliminate that diffusion limitation? And how can we do that? So in solution electrochemistry, double layer determines the rate of the reaction for diffusion limited. Size of the double layer determines the rate of the reaction for diffusion limited reaction, right? So if we make thin double layer, or if we reduce the size of the double layer so tiny to be so tiny, we will literally eliminate this peak shaped voltammogram forming phenomenon from the picture. So that's what we do when we stir the solution, or when we rotate the electrode, or when we reduce the electrode size to be so small that the double layer size will also almost become negligible. For example, using ultra micro electrodes with electrode surface area in a few or fractional micrometers. So those are the cases where we will have effectively eliminated double layer, and the voltammograms, whatever you see, will be just sigmoidal. It will have a perfect reversibility without forming any peaks. Even in cases where the ultra micro electrodes tip is so tiny, like of the order of few tens of nanometer, you won't even see some hysteresis like this. The backward sweep will exactly superimpose on forward sweep. So this is very important for studying certain reactions, which I'm not going to talk about now. So that's what happens when you have a diffusion limited reaction with a sufficiently thicker and larger double layer. So now you know that. Let's see about effect of scan rate. The scan rate is nothing but how fast you drag this potential from point V1 to point V2. So if you drag it at a very high rate, for example, so we give we give numbers for this scan rate: 10 millivolt per second, 50 millivolt per second, 100 millivolt per second. So what does it mean? So you are dragging that potential. If it is 100 millivolt per second, you are dragging up to 100 millivolts from the point where you have begun. So that's what it means. So when you change this rate, the potential ramp rate or scan rate, what happens to the voltammogram? Let's take the same linear sweep voltammetry. So with increasing scan rate, it says that the peak current will increase. Why does it increase with the increasing scan rate? And that is the question. So it is explained clearly by the Fick's law of diffusion. Fick's law of diffusion states that the flux here is meaning the amount of electroactive species reaching the electrolyte surface. So when you apply a very low scan rate, okay, so you are giving the interface sufficiently longer time to grow a thick and thicker double layer, which means that with increasing double layer thickness, the amount of flux reaching the surface, flux of electroactive species reaching the surface of the electrode will be lesser. So that's why with the lower scan rate, you get lesser current. With a higher scan rate, you get higher current. And for a perfectly reversible reaction, the peak current will be increasing as long as you increase the scan rate. Okay. And for CV, cyclic voltammogram, where you also reverse the potential back to V1, you will see a similar behavior. So depending on what happens to the peak current, peak to peak potential difference, and onset potential, halfway potential, with increasing scan rate or with changing scan rate, you can classify the reaction that you are studying to be in three different categories. One is reversible, second one is quasi-reversible, and the third one is completely irreversible. So let's see what are the conditions, how they are detected. So when I say reversible reaction, there are also two different kinds of reversible reactions. One is a reaction which is occurring with freely diffusing ions. So what do I mean by freely diffusing ions or freely diffusing electroactive species? This is very simple. So from Debye-Huckel theory and ion-ion interactions, solute-solvent interactions, you have read about ionic atmosphere and all those things, right? So in in combination with that theory, we introduce electrochemical double layer theory. So the moment you apply a potential, an electroactive species, which is now surrounded by solvent molecules, is approaching the electrode interface. And as soon as it approaches the electrode's interface, the salvation shell or ionic atmosphere around that electroactive species will distort because of the influence of the applied potential. So in that case, the electroactive species inside that salvation shell or ionic atmosphere will be squeezed out to specifically interact with the electrode surface, and that is called those kind of electroactive species and ions are called specifically absorbing ions. For any ions or any electroactive species that won't lose their salvation shell or ionic atmosphere when they are attracted by the applied potential, even when it is in the interface of the double layer, they are called freely diffusing ions. So these kind of ions and electroactive species are following the Randall-Sevcik equation. So if you just plot the peak current against the square root of the scan rate, they will be linear. So that's the primary indication that your reversible reaction, which has met all these characteristics, is completely reversible, and the electroactive species in the solution is not losing its salvation shell or ionic atmosphere. So that's how we distinguish a freely diffusing electroactive species from a specifically absorbing electroactive species. So you can ask me, what happens to the peak current to scan rate or square root of scan rate relationship if the electroactive species, the ion, is specifically absorbing on the electrode surface by losing its salvation shell. So this is the equation that dictates the relationship. According to this equation, you will see that the peak current will vary only with the scan rate, not the square root of the scan rate. So whenever you do scan rate dependent CV, you will have to plot two plots, one with peak current against square root of the scan rate, one will be peak current against the scan rate. So whichever is linear will give you the nature of the electroactive species that you are dealing with in your reaction, provided that they are all meeting all these conditions. The peak to peak separation should be closer to 59, peak position is scan rate independent, and the peak current ratio should be equal to 1, and current will linearly increase with the scan rate for the specifically absorbed ion. For freely diffusing ions, it will be peak current plotted against square root of scan rate. So these are the conditions. So what happens to the reaction rate? So we have been talking only about scan rate so far, assuming that the reaction rate is so high that even the lowest scan rate, whatever we are going to apply, is also not going to make any difference on the reaction rate. What happens when your reaction rate is lower than the scan rate you apply? So that's when you see these kind of features in your voltammogram. With the decreasing rate constant of your reaction, even with the same scan rate or with the increasing when you decrease the scan rate, you will see a cathodic shift in the peak potential. When you increase the scan rate, you could have increased the potential so fast before the reaction could even complete the first rate remaining step. That's when you see a shift in peak potential. So these are indications for the reaction rate being very slow. So this is something you can do with LSV or CV, and same phenomena can also be observed with cyclic voltammetry. So let's now see what is a quasi-reversible reaction and how can it be identified by performing a scan rate dependent cyclic voltammetry. So it is very simple. All that you are going to do is you are going to change the scan rate such as the one shown here, and you are going to see what happens to the peak to peak separation. So peak to peak separation I'm talking about is this, the cathodic peaks potential and anodic peaks potential. So what happens to this difference? Does it increase with the increasing scan rate? Voila, you have now landed up with a reaction that is quasi-reversible in nature. It will always be greater than 59 millivolt. To be precise, it will be greater than 120 millivolt actually. The peak position is scan rate dependent. That's what we are talking about. The peak to peak current ratio will never be equal to 1. Some of the reduced species or some of the oxidized species will stay oxidized or reduced no matter what or how many number of times you cycle the solution with your electrode and applying the same potential window. The current will also linearly increase with the scan rate. So just like the adsorbed ions. But in this case, the peak-to-peak separation will not increase, and peak current ratio, peak current ratio will stay uh, at 1. Okay, so again, so there is another thing, we'll talk about that later. Let's see the effect of scan rate on an irreversible reaction first. So what is an irreversible reaction? So there is no such thing as an irreversible reaction. Given if you are able to give all the requirements that is needed for the reaction to be reversed, everything can be made a reversible reaction. But in the context of electrochemistry, what we are talking about here, that you apply the same magnitude of potential for the same amount of time in opposite signs, it should be reversible. So in that sense, for any reaction that has only reduction peak but no oxidation peak or merely visible oxidation peak, they can be called irreversible reaction. There are many examples for this kind of reaction, and these kind of reactions are seen when the products escapes the solution. For example, gas evolution reaction. So when you perform chlorine evolution reaction, you oxidize chloride anion to form chlorine gas, and the chlorine gas escapes the solution. You don't have chlorine there to oxidize, to reduce it back to chloride. So you will not see a reduction peak for chloride, chlorine reduction. So that's an example for in an irreversible reaction. But in some cases, the reverse reaction, the opposite reaction, if you have done a reduction, the oxidation could be kinetically so slow that with the scan rate you have maintained, it could have not been possible to observe the change. So what can you do in such cases? That you can vary the scan rate. You can try reducing the scan rate, and if you can see the emergence of the reverse peak with the lowest scan rate, you can actually use this phenomena to find out the rate constant of the reaction. So with the highest scan rate, you don't give the interface enough time for the reverse reaction to occur. So that's why you are not seeing any peak here. But when you reduce the scan rate down low, you could actually see an oxidation peak. Even if you reduce it even further and match with the scan rate, which is equivalent to the reaction rate of the opposite reaction, you will see the same peak-to-peak current ratio to be 1. So using that information, you can actually calculate the rate of electron transfer. So effect of IR drop. So IR drop is nothing but IR here represents the potential drop. We know that in every DC circuit, the only element that forbids or that impedes the flow of charge is a resistor. So where there is a resistor, the current will drop, and when you multiply current with resistance, that will give you a potential drop. So when there is such an IR drop, even for a reversible reaction, the scan rate effect would appear to be something like this. With increasing scan rate, the peak-to-peak separation increases, which is now confusing, because I have told you that for reversible reactions, the peak-to-peak separation should stay constant and it should not exceed more than 59. It should stay very close to 59 millivolt to be called as a reversible reaction. This happens when there is a huge resistance in the solution. It could be due to poor electrolytic conductivity or poor electronic conductivity of the electrodes used. So in that case, what you can do is that you can measure the uncompensated resistance using impedance, and you can perform IR drop compensation, which can help you to remove some of these manifestations of IR drop from a reversible reactions cyclic voltammogram, and you will see the peak-to-peak separation stays almost the same until you reach certain higher scan rate values. So this is an indication that your reaction is actually reversible, but it shows, it appears to be like a quasi-reversible reaction because of IR drop. So what else you can do about this IR drop is that you can try improve the conductivity of the electrolyte, you can try improve the electronic conductivity of your electrode, which can result in different features for the same reaction for the same analyte. So that's what happened here. So here you see IR drop uncompensated with a supporting electrolyte concentration of 50 millivolt, and this is IR drop compensated for the same. But when you increase the supporting electrolyte concentration 5 times, you see even without IR drop compensation, we see a similar phenomena. So this means that this happened because of poor electrolytic conductivity, and that's why it appeared to be like a quasi-reversible reaction, when in fact it is not. So these are something that we should be always conscious about. And for kinetically controlled reaction, irreversible reaction, such as hydrogen evolution reactions and oxygen evolution reaction, as long as you increase the potential, the current will keep on increasing, given that there is no other medium of making the reaction to be diffusion limited. So in extreme pH conditions like highly alkaline medium, highly acidic medium, these two reactions are completely controlled by the kinetics of the reaction. So as long as you increase the potential, you will see increasing current. And HER and OER voltammograms will never have a peak in their kinetic turnover region. So these are some examples. But if you have both diffusion controlled phenomena and a kinetically controlled phenomena in the same window, potential window, you will see the effect of scan rate to be even more beautiful. So this is an example of methanol oxidation reaction with a copper oxide hydroxide electrode. So in which the copper hydroxide and oxide should be oxidized to copper 3 plus, forming copper oxide hydroxide before the methanol oxidation can be done. So this oxidation reaction of copper 2 plus to copper 3 plus is diffusion limited. That is why with the increasing scan rate, you see an increase in peak current. But this is the MOR part, which is kinetically controlled at these potentials, so that it does not get, they do not get affected by the increasing scan rate. Even for the lowest and the highest scan rate, the peak current you see at the vertex potential is the same. So this is a beautiful technique. I mean, scan rate effect to see which is diffusion control, which is not diffusion control. So using this thing, you can actually say how your material is behaving at the interface. And that's it. Let's now move on to part 3. So, part 2. We have just 10 minutes. I'll try to give you a very quick overview of impedance analysis, which you may find useful. So electrochemical impedance spectroscopy, it is an AC technique. So the voltammetric techniques, whatever we have seen so far, are DC techniques. This one is an AC technique. So in this case, what we do is that we take an electrode and insert that electrode, immerse that electrode in an electrolyte solution. As soon as we do that, it establishes a DC potential. Okay, no matter what potential is there, it could be open circuit potential, or you can also imply any other DC potential. Now the DC potential is established at the interface. What we are going to do is that we are now going to disturb that interface and the DC potential that is already established by applying an AC perturbation potential. So when I say AC, the polarity changes with time and we call it frequency. And it can be from 1 megahertz to 0.1 millihertz. So it depends on the reaction what you are studying. So we have an electrode inserted in a solution which established a DC potential, and that DC potential is now disturbed or perturbed by the AC potential what we are going to apply. And the AC perturbation potential can have a magnitude ranging from 5 millivolt to 1 millivolt. What does it mean is that if the DC potential is 0, if I apply AC amplitude of perturbation 1 volt, this potential will be changed by plus or minus 500 millivolt or 0.5 volt, and the frequency of this change is determined by the frequency what we apply. If it is 1 hertz per second, 1 hertz, for example, if it is 1 hertz, which means that it can switch this polarity for 1 second for 1 time. If it is 100 hertz, it will be 100 times, just like that. So depending upon how fast we change this polarity, the interface will also act accordingly. So in DC, we had only one resistor that was impeding the current, and that is resistance. We call that resistance. But in AC circuit, we have resistors, capacitors, and inductors. So you could also argue with me, we also talked about capacitance current in DC techniques. Why cannot those capacitance and capacitors can impede, why cannot they impede the flow of electrons or charge? Yeah, it is true that there are capacitors, but if you see, as soon as you apply a DC potential and keep it for a while, the first thing that happens at the interface is that charging of the double layer. So that happens through the resistor that is already existing. So first thing is that charging of the double layer. Unless otherwise this double layer is charged by 63.2% of its entire capacity, no electron transfer can happen. So this is kind of a systematic error in all DC techniques. Unless otherwise you do the capacitance correction like you do for IR drop compensation. So this is always there. But in the case of AC technique, as we keep on changing the polarity, by applying a AC potential, the capacitor element is never out of picture, or the inductor element is never out of the picture. We'll see in the next slide. So this is the principle. So this is the Ohm's law for a DC circuit, and this is the Ohm's law for an AC circuit. The R here is replaced by the letter Z, because here the Z represents the may I continue? Yeah, thank you. I'll continue. Yes. So the Z here is in place of R for the DC circuit. Z represents the combined opposing force or impedance put in front of the flow of charge in an AC circuit. This is the combination of resistance from capacitor, and resistance from resistor, resistance from inductor. So that is when this can be converted. Just a second. So when you do that, this same Ohm's law can be modified into this thing, and where we see that for any change in the frequency will also change. We also see a change in the current potential response. So in conventional electrochemical impedance spectroscopy, with the AC perturbation applied, this magnitude tells about plus 0.4 to minus 0.4 is the AC perturbation, and this is the time. So the current potential relationship appears to be an ellipsoidal one. So from this, it is very, very difficult to guess what is happening. So, what is happening there, right? So that just represents one dot from a point. So since it is to be imagined in space, the complex expression is brought into a picture in order to avoid the complexity that was there with the Lissajous representation. So in mathematics, people use this Euler formula to convert these coordinates into Cartesian coordinates, where we can use three axes, ABC axis, are the polar coordinates. But using polar coordinates is more comfortable in this case, because pointing an impedance in an imaginary axis because of complex expression in polar coordinates is easier. So this is for just one applied frequency, and if you vary the frequency, you will get a plot such as this one from high to low. So this is the conventional Nyquist plot you get from performing electrochemical impedance spectroscopy. So before going into see different plots, let's now establish the characteristics of the circuit elements. The resistor has no imaginary part, because this is the true thing that is actually impeding the current or flow of electrons or charge at all the time. It exerts zero phase between potential and current, which means that the magnitude can be different, but they will never go out of phase in space. Okay, they will always stay on the plane of the same axis no matter what, if you passed a current or electron or charge through a resistor. In the case of capacitor, it has a real part and it also has an imaginary part, and it exerts 90 degree phase shift. If your real part is on the x-axis, it will be either on the y-axis or z-axis, the imaginary part. And in capacitor, the current always leads potential. It is because when you immerse an electrode in the electrolyte solution, the first thing that happens is the adsorption. So when the adsorption of ions happens, it contributes to some current, non-Faraday current. That's why in capacitor, the current always leads the potential. The reactance or impedance of an inductor is a phenomena that results from magnetic material. So when you insert an electrode into an electrolyte solution, which is also magnetic and have several unpaired electrons to induce magnetic movements, and if you imply a DC potential, the first thing that happens is the rearrangement of orientations of those free electrons that can impart magnetism in that material. So when you apply an AC perturbation, you also disturb that orientation, right? So that orientation will also keep on changing, just like the double layer is charging and discharging. So all these three phenomena can impede the flow of electrons. That is why we have these three combined opposition for the flow of charge in an AC circuit, and we call it impedance. So in the case of inductor, the potential always leads I. It is just like how current leads potential in capacitor, because in capacitor, the moment you insert the electrode, absorption of ions takes place, which contributes to current. But in the case of inductor, the electrode is already having unpaired electrons. The moment you insert that electrode with unpaired electrons, it establishes a double layer. That double layer has a potential, and that potential will rearrange the orientation of those unpaired electrons, giving you a reactance due to inductor element, and in which the potential leads the current. So if you see any impedance response where the potential leads the current, and you can blindfoldedly say that my circuit has an inductor element. So just like that. But the most important point to remember here is that the capacitor, it acts as a short circuit at a very high frequency and open circuit at a low frequency. You need to understand this particular phenomena in order to understand your Nyquist plots. So at high frequency, what happens is that you are changing the potential at the interface so fast that the charging and discharging of the double layer literally becomes to a halt. It is not happening anymore, because you are so fast that your interface's potential is now your interface is not able to cope up with that speed. So there is no charging and discharging, and it acts as a short circuit. But at low frequency, you are giving enough time for the absorption and desorption to occur, so that the capacitance tends to be as high as possible depending on how low your applied frequency is. In the case of inductor, induction, as I explained you already, it's just the change in orientation of the unpaired electrons, which are responsible for the magnetism in the material. So this happens so quick, even faster than the highest frequency you can think of. So what happens is that at the highest frequency, the reorientation occurs at the equal rate. So the reactance due to inductor element, or impedance due to inductor element, is also tend to be very, very, very high. But at low frequency, what happens is that the moment you apply a low frequency like 0.1 millihertz, so the AC potential is now staying at a particular potential, and as soon as it goes there, the reorientation is already completed, and it is going to stay there for a while, and the reorientations are not happening, which means that is not impeding the flow of current anymore, because the reorientation is already completed. So it acts as a short circuit. Because inductor and capacitor have their imaginary path exactly opposite to one another, at highest frequency, the capacitor cancels out inductor. At the lowest frequency, at the highest frequency, the inductor cancels out capacitor. At the lowest frequency, the capacitor cancels out inductor. So at the highest frequency point and at the lowest frequency point, the only circuit element that is impeding your electrodes charge transfer characteristic is this guy, the resistor, which means that the impedance point at these two highest and lowest frequencies are literally the resistance, not impedance. And that is why whenever you have a Nyquist plot such as this one, you say that this is solution resistance, and this is the combination of solution resistance and charge transfer resistance. Even though you know that it is an impedance plot and it should not be called as resistance, we should call it impedance, but we call it resistance because here at the highest frequency, the inductor cancels out capacitor. At the lowest frequency, the capacitor cancels out inductor. So only existing circuit element here is the resistor. That's why we call them resistance. But if you move anywhere on this arc of semicircle, those are not resistance, those are impedances. Clear? Now let's get back to the type of plots you can get from. Oh, sorry, I'm exceeding my time. I'll try to finish. Yes. So types of plot: Nyquist plot, Bode impedance plot, or to be specific, absolute impedance plot, and Bode phase angle plot. So the same information you can get even here, but it gives you even more information about the frequency, which is not there in the Nyquist plot. So if you want to know when exactly this reaction starts and what is the RC time constant, how much time that does the electrode electrolyte interface requires to charge its capacitor by 63.2% to begin the electron transfer. These two plots are more important than this one. And these are some Nyquist plots for different kind of reactions. When you have only a charge transfer control reaction, all that you get is a semicircle, depressed semicircle. And for more than, if there are more than one type of reaction happening on the surface, or if there are more than one type of catalytic sites on your electrode, each of them will give you a distinct semicircle. So that's how you can guess. And if there is a diffusion limitation, it will also have a Warburg component, which can be seen with the a slanted line, either more than 45 degree angle or less than 45 degree. But it is mostly more than 45 or exactly 45. When it is exactly 45, we call them diffusion limitation phenomena. Or when it is just more than 45 degree, we call it constant phase element. Because to be qualified, to be called as a capacitor element, it should have an angle of 90 degree. We have just seen, right? So no real time electrode electrolyte interface will have that angle, because we will not be able to create a perfectly smooth planar surface. There will always be some surface roughness, and that will contribute to some manifestation in the capacitance behavior, and that will result in an angle for a Warburg component lesser than 90 degrees. So for people, those who are working in supercapacitor, even though you are working only with EDLC, only with carbon, you will never get an angle of 90 degree. It can be 85, 86, 87, but not 90, because your surface will never get that smooth and perfectly planar. Yes, so this is one thing that I want to tell you clearly. So please pay close attention here. So this is an OER CV, oxygen evolution reaction CV of a stainless steel electrode. Okay, so this is the open circuit potential. This is the zero potential versus HHO, and this is the potential where the oxidation of metals in stainless steel electrode takes place, and this is the potential where the OER starts, and this is the potential window where only OER occurs. So I have recorded impedance at all these points and also for this whole region, and you can see how do they look. So when at OCV there is no electron transfer, it is just adsorption and desorption. All that I have, which is limited by diffusion, all that I have is a line, just a line, not a semicircle. So this is the Warburg component, and the angle is more than 45 degree and closer to 90 degree, which means that there exists a constant phase element, CPE. At 0 degree, we still don't see any reaction happening, electron transfer happening. So you will see a similar line. So this is again indicating mere capacitor behavior. At 0.45 volt, so here, so what we see is that oxidation of nickel and iron. So that is a diffusion control process. Not only that, it is a stainless steel electrode, which is also having a chromium oxide corrosion resistant layer, protecting nickel and iron from corroding away. So there you see oxidation and oxidation phenomena with the semicircle, and the oxidized nickel and the iron tend to go away and redeposit. So whenever you see a loop, that indicates the corrosion and redeposition, dissolution and redeposition of the metal on the surface. So when you at the onset, so the potential is at a bare minimum, so you have a very high charge transfer resistance because you have reached the kinetically controlled region, but the potential is not so high enough. But when you increase the potential gradually in this region, your charge transfer resistance keep on decreasing. So that's the beauty of electrochemical impedance analysis and how it can help you understand what is happening in your electrode electrolyte interfaces. Yeah, so things you get to know from your EAS analysis is the RCT, the cutoff frequency, and admittance at the lowest frequency. All this can be helped. All this can help you to give more knowledge about how your electrode electrolyte interface behaves for the reaction that you are studying. So for further reading, I always suggest these 3 books. And thank you so much for being so patient despite the interruptions. If you have some questions, please fire at me. I will be happy to answer.
Thank you, sir. Thank you, sir. Participants, please, this is the interaction time.
If you have a question, you can also type them in your chat box. I will be happy to read and answer.
Sir, there is a question in the chat box.
What is the purpose of equivalent circuit fitted in the EAS? Yeah, there is no purpose, really. So if you have seen any of my recent papers, you will not see a single EAS circuit. There is a famous saying that even that you are not restricted for having enough circuit elements, you can even fit an elephant. You can even make a circuit element, combination of circuit elements for an elephant. There is no meaning of making such EAS fitting. I never do that. In fact, I don't usually use Nikos plots. I always go with the absolute impedance plot and phase angle plot. These two plots will give you all the information that you need without making any iterations with the help of a software. When you can do this with by just plotting two simple plots, absolute impedance plot and body phase angle plot, why would anyone want to buy software which can do that with a Nikos plot, which is also inferior to the body plots? So I never do that. Thank you. And please don't do that. Yes. If any reviewer asks you, you just let me know. I will write the rebuttal. Anything else?
Sir, what is the software?
I don't know the name. They use something called I think it is ZFit. I don't use it, so I don't remember it. Sorry.
One more question.
Yeah.
Can you show or tell Nikos plot formula?
Nikos plot formula?
They are posted. Sir.
So there is nothing called Nikos plot formula. Nikos plot is nothing but it's a plot of the imaginary part of impedance against the real part of impedance. There is no such formula. I'm sorry if there is anything and I have missed it.
Okay, sir.
Yeah.
Any questions from the participants? Okay, sir.
Yeah, thank you, madam. Thank you for giving me this opportunity. I thank the head of the Department of Physics and the GVG, Visalakshi College for Women for this opportunity. It is always a pleasure for me to talk about electrochemistry. So thank you so much. Yeah.
Really, your session is very informative, sir.
Thank you.
Because we have started our work in our using this electrochemical outstation. So our research scholars gained more information from you.
Oh, that's really great to know.
We will contact you through.
Yeah, sure. You're welcome. You're welcome to contact me at any time. Just give me an email. I'll be in touch with you.
Yes, sir. Yes, sir. On
Thank
behalf of our.
Hello.
Yes, Miss Pavitra.
Hello.
Yeah.
சார் இப்போ சில ரிமூவல்ஸ் எல்லாம் வந்துட்டு அந்த ஃபிட் பண்ண கர்வ் போட்டு டயக்ராம் போட சொல்றாங்க. சில பேர் வந்துட்டு அந்த EASல வந்து ஸ்டெபிலிட்டியும் அதுவும் வந்து கம்பேர் பண்ணி போட சொல்றாங்க. ஸோ எப்படி சார் அது ப்ரெசென்ட் பண்றது EAS போடும்போது?
ஒரு விஷயமா ஃபர்ஸ்ட் வந்து நீங்க EAS ஃபிட்டிங் சர்க்கியூட் இருக்குது பாத்தீங்களா, EAS சர்க்கியூட் அதை போடணும்னு அவசியம் இல்லை. ஏன்னா தட் இஸ் நாட் கிவிங் யூ எனிதிங். அதுக்கு பதிலாக நீங்க என்ன பண்ணலாம் அப்படின்னா, ஒரு போர்டே பிளாட்ஸை போர்டே அப்சல்யூட் இம்பிடன்ஸ் பிளாட்டையும் ஒரு போர்டே ஃபேஸ் ஆங்கிள் பிளாட்டையும் இப்போ ஈக்குவலாக பிளாட் பண்ணி அதில் உங்களுக்கு என்னெல்லாம் இன்ஃபர்மேஷன் ஃபிட்டிங்கில் கிடைக்குமோ அது எல்லா இன்ஃபர்மேஷன் இது ரெண்டுத்துல இருந்து எக்ஸ்ட்ராக்ட் பண்ண முடியும். ஓகேங்களா? அதை வச்சு நீங்க ரெபுட்டல் கொடுத்துடலாம். ஃபர்ஸ்ட் திங். செகண்ட், ஸோ ஃப்ரம் இம்பிடன்ஸ் how can you tell it is stable, right? That's your second question. So what you should do is நீங்க ஃபர்ஸ்ட் வந்து ஒரு ஸ்டெபிலிட்டி ஸ்டடி ரன் பண்ணணும். இட் கேன் பி CA ஆர் CP, க்ரோனோ ஆம்பியரோமெட்ரி ஆர் க்ரோனோ பொட்டன்ஷியோமெட்ரி. அதை ரன் பண்றதுக்கு முன்னாடி ஒரு இம்பிடன்ஸ், ரன் பண்ணதுக்கு அப்புறம் ஒரு இம்பிடன்ஸ், ரெண்டு இம்பிடன்ஸ் இருக்குங்க. Then compare these two impedance and see if there is any change in charge transfer resistance. If there is no change, that means your material is stable, it is stubborn, it is rugged. If there is a change, if there is an increase, your material is not so stable. It is undergoing some sort of deactivation. If the resistance has decreased, it is even better that your material has actually been activated because of this stability test. So this is how you can interpret your impedance results before and after stability studies.
இன்னொரு டவுட், அந்த ஸ்டெபிலிட்டியில சில பேருக்குலாம் 114 சம்திங் அந்த மாதிரி பர்சன்டேஜ் ரிப்போர்ட் பண்றாங்க. ஸோ அது எப்படி வந்து பாசிபிளா இருக்கும்?
எஸ் இட் இஸ் வெரி சிம்பிள். அந்த பர்சன்டேஜ் வந்து எதை வேணாலும் குறிக்கலாம். இப்போ வந்து பாத்தீங்கன்னா ஸ்டெபிலிட்டி வந்து இப்போ நீங்க சிஏ பண்றீங்க, எலக்ட்ரோனாப்ரோமெட்ரி பண்றீங்க, யூ ஆர் அப்ளைங் சம் பொட்டன்ஷியல், ரைட்? ஸோ த மொமெண்ட் யூ அப்ளைட் பொட்டன்ஷியல், உங்களோட இன்டர்ஃபேஸ் வந்து 100 மில்லியம்பியர் கரண்ட் கொடுக்குதுன்னு வச்சுக்கோங்க per centimeter square. ஸோ ஆஃப்டர் 12 hours that 100 milliampere has reduced down to 90 milliampere. So இப்போ எவ்வளவு லாஸ் இருக்குதுல? Can you give me a percentage?
100ல இருந்து 90 டிக்ரீஸ் ஆகுது.
டிக்ரீஸ் ஆயிருக்கு. எவ்வளவு பர்சன்டேஜ் லாஸ் இதுல நமக்கு?
எவ்வளவு ஃபர்ஸ்ட் பொட்டன்ஷியல் டிவைட் பை எவ்வளவு லாஸ்ட் இருக்கோ இந்த 100
ஃபர்ஸ்ட் கரண்ட் அதேதான். சோ you see 10% லாஸ். ஓகே, அதுதான் அந்த பர்சன்டேஜ் அவங்க சொல்றது. இதுவாவும் இருக்கலாம் அல்லது
அல்லது அப்படிங்க
100% சொல்லுங்க.
100% தானே சார் கால்குலேஷன் போடுறோம். ஸோ இப்போ ஸ்டார்டிங் வந்துட்டு அவங்களுக்கு வந்துட்டு ஒரு 100 வந்து கெப்பாசிட்டன்ஸ் வேல்யூ வருதுன்னா இவங்களுக்கு முடியும் போது ஒரு 150 அப்படின்ற மாதிரி ரிப்போர்ட் பண்ணிருக்காங்க. ஸோ இப்போ இன்க்ரீஸ் ஆயிருக்கு அந்த மாதிரி. அப்போ வந்துட்டு மீனிங் என்னன்னா ஸோ ஒரு குறிப்பிட்ட சைக்கிள்ஸ்க்கு அப்புறம் ஆக்டிவேட் ஆயிருக்கு.
எக்ஸாக்ட்லி அதுதான் அதுக்கு மீனிங். There is no other meaning. After some number of cycles the interface actually got activated. அது மட்டும் இல்லாம இதுக்கு ஆக்டிவேஷன் மட்டும் காரணமா இருக்க முடியாது. there are many other reasons. ஃபார் எக்ஸாம்பிள் வெட்டபிலிட்டி ஒரு இஷ்யூவா இருக்கலாம். இப்போ நீங்க ரைட்டாவே எலக்ட்ரோட உள்ள வச்சு அப்படியே நீங்க ஸ்டெபிலிட்டி ஸ்டார்ட் பண்ணீங்கன்னா அது வந்து இனிஷியலா இப்போ சார்ஜ் டிஸ்சார்ஜ் நீங்க ஸ்டார்ட் பண்றீங்கன்னு வைங்களேன், இனிஷியலா வெட்டபிலிட்டி கம்மியா இருந்திருக்கலாம். ஸோ வித் டைம் வெட்டபிலிட்டி இன்க்ரீஸ்ட் அண்ட் கெப்பாசிட்டன்ஸ் வில் ஆல்சோ இன்க்ரீஸ். அது ஒரு ரீசன். ஸோ இட் வில் நாட் பி கால்ட் அஸ் ஆக்டிவேஷன். இட் இஸ் ஆக்சுவலி mere manifestation of increasing wettability. So there are more than one reasons for that. So இன்னும் இந்த பர்சன்டேஜ் அதுக்கு தான் சில பேர் என்ன பண்ணுவாங்கன்னா, so they will wait until the capacitance reaches its maximum and they will take that point to be 100%. From there they will calculate the loss in capacitance after performing few more number of cycles.
Okay.
Yes.
Okay.
Welcome.
Thank you, sir. Question from Mohan Raj, sir. How will you differentiate faradic and the non-faradic process?
So there are many ways. With all the techniques I have given you, you can do it. Even with a simple CV, you will not see any peak for non-Faraday current. So it will be a mere almost a perfect rectangle. If there is a Faraday process, and whether it is diffusion limited or kinetically controlled, you will see an increase in current, an onset potential, halfway potential, diffusion limitation potential, a peak potential. All these things will be seen only when there is a Faraday process. So with non-Faraday process, you will not see anything. You will see just a line, and you will see another line. So it will be a rectangle response.
Thank you, sir. Thank you, sir. Formal vote of thanks.
Yeah, please.
On behalf of organizing committee, I would like to express my sincere gratitude to our guest, Dr. Anandraj Sengani, Assistant Professor, Department of Chemistry, IIT Kanpur, Associate of Indian Academy of Sciences, Bangalore. Thank you, sir, for the interesting and highly informative speech. I would like to thank all the participants for their patient listening. Finally, I thank my colleagues for their support and dedication. Once again, thank you all.
Thank you, sir. Thank you very much, sir.
Thank you, madam. Thank you so much. And thank you for being so patient with all the interruptions. So I'm at home, so these things happen all the time. Even with the group meetings I conduct with my students and the meetings that I have with my collaborators, all are being disturbed by my girls at home. So I'm sorry.
Sir, information எங்க இருந்து எப்படி வந்தாலும் கேட்டுக்கலாம் சார்.
Thank you very much. Thank you.
Thank you.